So I'm going to just add a few more details to the things we have touched on, just to orient ourselves slowly towards atmospheric circulation and then ocean circulation. So we talked a lot about Clausius-Clapeyron, and I want to touch on it a little bit because in the atmosphere that's one of the biggest nonlinearities, other than the baroclinic instabilities that happen in the mid-latitudes, which we will not discuss in too much detail. So here we are looking at an example of a flask which is measuring its temperature. So it's got 1 kilogram of dry air with 5 grams of water vapor, and there is water sitting at the bottom at 25 degrees centigrade. The saturation mixing ratio at 25 degrees centigrade is 20 grams for one atmospheric pressure of 1 unit. H2O, typically it's 1 sea level pressure, 14.5 pounds per square inch or 1000 hectopascal, depends on how you say it. H2O water vapor content is at 5 grams. Relative humidity, if you have kept the water vapor content at 5 grams and the total holding capacity is 20 grams, then your only relative humidity is specific humidity divided by saturation humidity, which is also called mixing ratio. So it's 5 over 20, so 25%. What happens? Saturation mixing ratio is again at 20 grams. If you raise the water vapor content to 10 grams, then your relative humidity goes to 50%. Of course, you can cool the temperature and increase the relative humidity as well, since the Clausius-Clapeyron relation between temperature and vapor pressure, we saw that either you can cool the air and bring it closer to saturation, or you can add more water vapor and bring it closer to saturation. So you have brought it from 25% to 50% by not changing the temperature but by adding more water vapor, and here you are adding all the way to saturation and reaching relative humidity of 100%. This becomes important in global warming as well, because with global warming we are increasing the air temperature on average, which means its water holding capacity goes up, so specific humidity goes up, but its saturation mixing ratio also goes up. So whether the relative humidity actually goes up or not depends on where you are. On the ocean, where there's lots of water vapor available, warmer atmosphere may just pick up more moisture and relative humidity may remain constant, whereas on land, where there is no constant supply of water vapor, relative humidity need not stay constant. So these are things that matter, because for precipitation processes and so on, relative humidity becomes very important. So this is for a place like Washington DC. We're just looking at the diurnal cycle, so you can see the temperature ranges are pretty cool here. So the lowest temperatures occur in the morning time, because during the day there is radiation and heating, so the heating by the radiation is much larger than outgoing long wave radiation. After sunset the heating drops, but the outgoing long wave continues, and at some point early in the morning outgoing long wave is dominating and creates the minimum temperature. So here, assuming there is no wind that's constantly advecting humidity either from the west or east, north, south, whatever, when temperature cools, relative humidity can go up because of what I said before. Clausius-Clapeyron is just moving you closer to the saturation by the cooling, so relatively humidity is increasing, and when the daytime warming happens and the warmest temperatures are reached as a balance of long wave and short wave, the water holding capacity or saturation mixing ratio has gone up, but the relative humidity, because humidity is not increased by advection, there is no source of water locally, so lowest relative humidity is reached around 6 p.m. So this gives you a sense of how weather can happen without if depending on whether you have winds coming in changing humidity, or if it's calm time with humidity being controlled locally by temperature changes on a daily time scale. So 50%. So here 10 degree Fahrenheit, 50 degree Fahrenheit or 10 degree centigrade is pretty cool temperature. So relative humidity falls to about 38%, which is quite dry, and it can reach over 70%, which is quite humid actually. So you can see large diurnal cycle here. You can look at it in another way. So if you think about the US, which is a large continent, you have cold sea surface temperatures here, as we will see a little bit later on, and winds are at this latitude coming from the west. They are called westerlies. So we'll see the trade winds, the westerlies, the easterlies, and so on in a minute. I'm jumping a little bit ahead to kind of give you a sense of how to think about it. And we are looking at temperature here for Eureka, California, and for New York City. So the maritime influence over California keeps the temperatures over Eureka, California fairly uniform, doesn't have a huge seasonal cycle. So that's the for example, if you go to Tasmania, which is pretty far south, but it is such a it's an island, has such a large maritime influence that it remains fairly mild even during its winter, whereas New York City, which is heavily influenced by continental winds, especially if the jet stream dips in, as we will see later, it begins to get huge seasonal cycles. So you can see that in the summer it's getting much warmer than Eureka, California, and in the winter it can get really blurry cold. This is hardly a typical winter. This is a long-term average. Okay, so this is another way that weather and climate get affected by how the winds are blowing and what influence you have, continental influence or maritime influence and so on. So maritime influence here also creates some very unique things. There is a statement attributed to Mark Twain, apparently he's not the originator of that, which says the coldest winter I experienced was a summer in San Francisco. So the moist air coming from the ocean hits the cold, cooler air over Eureka, and then it can reach saturation. So low-level clouds or fog gets formed because of that advective moisture. It's called advective fog. So San Francisco Golden Gate Bridge is very famous for its advective fog during the summer months. You need humidity, so summer is winds from the ocean help bring humidity, but the cold continental temperatures related to the cold coastal temperatures help create fog or take relative humidity to near saturation and create fog. Okay, if you on the other hand also look at rainfall distribution, this also is, so here are some mountains which create orographic rain. We saw that these westerlies, when they are forced to climb the mountains, they put a fair amount of rain. But if you come to the southwest, where there is no such situation, there are mountains inside which have some rain, as you can see here. These are very dry places, and this is where a lot of the drought problems now exist. So you can see the stark rainfall contrast across California, and it's fairly dry, and this is related to again cold temperatures but orographic rain. Lots of dry regions in the middle of the country, rainfall of the order of 10 inches or lower, but the ocean warm waters coming up here and the warm Gulf of Mexico waters along with the westerly winds together produce quite wet and stormy weather over here. Most of the east of the Mississippi River is kind of running down here, and you can see that they get rain that is much higher than over here, especially more than here. Florida, of course, gets quite tropical, and so do the coast of Gulf of Mexico, Alabama, Mississippi, Louisiana, Texas. They are really muggy, wet places. Okay, if you move to a place like Mumbai, temperature doesn't change much. It's very warm throughout the year. March, April, May gets slightly warmer. During the rain it gets cooler, then gets warmer again because there is always sun shining. Tropical sun is very warm. So you can see the rainfall maximum happens during the monsoon from May into June, July, August, and then drops off. It doesn't get much rain at all during the rest of the year. So temperature remains the same, and relative humidity also remains fairly high. The cooling in the winter months drops it a little bit, but still over 60%, and during the rainy season it can get over 80% relative humidity, and you can imagine just how muggy it is when you combine it with this warm temperature. This is the distribution of rainfall, which again gives you a sense that there are Western Ghats here, which is the mountain range. There is Himalayas here, so very high rain over here, desert over here, moderate amounts of rain here. Rain here is coming in a different season, and so on. So the point is really to show that before we move to sea surface temperatures, rainfall distributions, visiting again the idea of moving energy from energy surplus region to energy deficit regions, all are going to play a role in determining the wind bands, which are going to affect the ocean and ocean temperatures and surface temperatures, rainfall distributions, humidity, and so on and so forth. So this is why I went through these simple examples of different weather regimes. We are talking about climate, but climate of San Francisco is that it's very cool in the summer months and much of the year, whereas LA, which is further south, can get very warm. Las Vegas is very hot, and so on and so forth. Okay, so we'll go into more specific climate processes in the next podcast. Okay.